Welcome students, hoping you all fine. I am Asma and I am here with the 8th program of calculus of BSCS level, which is about graphing of functions. But before going to today's program, let me briefly explain that what we have studied in our last program. In our last program, we studied functions, some operations on functions like sum, difference, product and quotient, expressing a function as a composition, and classification of functions. Now, after having the concept of functions and some operations on functions, we are able to move further to the graphs. So today we will study graphs of function, graphing function by translation, graphing function by reflection, graphing function by scaling, a vertical line test, even and odd functions. We will start today's program with the graph of different types of function. Here we will show that how to represent functions geometrically by graphs. Such graphs provides a very useful way of visualizing the behavior of any function. We shall also develop some basic techniques for using graphs of simple functions to construct graphs of more complicated functions. Let's start with the definition of graphs. Graph in xy plane of a function f is defined to be the graph of the equation y is equal to f of x, where y would be the dependent variable, x would be the independent variable. Now we shall consider different functions and then understand the procedure of drawing graphs. To understand the procedure of graph, you can see an example on the screen. For this example, if we have to draw the graph of a function f of x is equal to x plus 2. So for the solution, first we have to put some values of x to get some values of y. By joining all these points, you get a straight line or you get the graph for the function f of x is equal to x plus 2. Here we will consider one more example to draw the graph, and that example is based on absolute function. You can see that example on the screen. If we have to draw the graph of f of x is equal to x modulus, which shows an absolute number, to draw this graph for all the positive values of x, we would be having all the positive values of y and with an increment of 1. So we would be having this line. And if we consider all the negative values of x, which would be definitely on the left hand side, so we consider some values of y. In this way, we will get this line for the graph. Dear students, we can draw two graphs on the same Cartesian plane as well. Now let's consider a graph of two functions on the same Cartesian plane. For example, you can see on the screen, phi of x is equal to x plus 2 when x is not equal to 2, and phi of x is equal to 6 when x is equal to 2. For the solution, if we draw the graph of the second function, here this dot shows the graph for the function phi of x is equal to 6. To draw this graph of the second function, which is phi of x is equal to x plus 2, where x is not equal to 2. Here we will put different values of x to get different values of y. So we put x is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3, and we get different values of y. As we have drawn the graph of this function in the previous example, we will be having this line. So through this method, we can draw the graph of two functions on the same Cartesian plane as well. Here we consider another example of graph of two functions on the same Cartesian plane. You can see that example on the screen. For this example, if we have to draw the graph of g of x, where g of x is equal to 1 for x less than or equal to 2, and g of x is equal to x plus 2 for x greater than 2. To draw this graph, we will consider different values of x. First, for x is less than or equal to 2. So even for minus 2, minus 1, 0, 1 and 2, we have the same y value, which is 1. To draw the graph of this function, we would be having this straight line. This dot represents that 2 is included in the graph of the function. To draw the graph of the second function, which is g of x is equal to x plus 2, as you can see that this graph is defined on all the values of x which are greater than 2. So by joining the points, we get the graph of x plus 2 over here. In all these examples, we considered some linear functions. Now we will be providing the quadratic functions and then their graphing by translation, which is the second topic of today's program. We will start with the definition of translation. You can see the definition of translation on the screen. Translation: when we add or subtract some constants in function or within a function, then it's called translation of x's. Some forms of translation can be y is equal to f of x plus c, y is equal to f of x minus c, y is equal to f of x plus c, y is equal to f of x minus c. Now after making the graphs of y is equal to f of x, which is considered as the simple function, we here can draw the graphs of closely related equations as well by translation. Here we consider a function with some changes. You can see an example of addition of a constant to the function on the screen. For translation, if we have a function y is equal to x square, so this dotted line represents the graph for this function. And if we perform an operation on y is equal to x square, and the operation is that we add a positive constant 2 to f of x. So the equation becomes y is equal to f of x plus 2. In this way, we get a new equation as y is equal to x square plus 2. The geometric effect of this change is translates the graph of y is equal to f of x up 2 units, as we have added 2 in the function. Let's again consider another example which shows the subtraction of a constant to the function. You can see that example on the screen. Again over here we consider the same function, which is y is equal to x square, and you can see this dotted line as the graph of y is equal to x square. We perform an operation over here that we add a constant 2 into f of x. So the resulting function is y is equal to f of x plus 2, and here the new equation become y is equal to x plus 2 whole square. And the geometric effect of this addition is that it translates the graph of y is equal to f of x left to 2 units. Here we consider an example of subtraction of a constant to the function. You can see that example on the screen. If here we consider the same graph y is equal to x square, so you can see this dotted line as the graph of this function. We perform an operation that we subtract a positive constant 2 to f of x. So our function become y is equal to f of x minus 2. And we get a new equation with this change as y is equal to x square minus 2. The geometric effect of this change is that it translates the graph of y is equal to f of x down 2 units. And you can see this change over here. Here let's consider another example of subtraction of a constant into the function. You can see that example on the screen. Here again, to draw the graph of y is equal to x square, you have this dotted line. We perform an operation that we subtract a positive constant 2 into f of x. So our function becomes y is equal to f of x minus 2. In this way we get the new equation as y is equal to x minus 2 whole square. The geometric effect of this change is that it translates the graph of y is equal to f of x right 2 units, which change you can see over here. Dear students, let's now consider one more example to understand the concept of translation, and here we will be considering a modulus function. You can see that example on the screen. As we did in the start, that we draw a graph of f of x is equal to x modulus. As I explained that for all the values of x which are greater than 0, we have the function value as y is equal to x, and for all the negative values of x which are less than 0, we get the function value as minus x. In this way, we get the graph like this. In the next figure, we will be performing an operation of subtraction. If we subtract a positive constant 3 to f of x, then our function becomes y is equal to f of x minus 3. In this way, we get a new equation as y is equal to modulus x minus 3. Here you can see that the change in the graph is that it translates the graph of y is equal to f of x right 3 units. And you can see that our graph is changed from origin to right 3 units. In the next figure, we will explain the addition and subtraction of a constant by translation. You can see that example on the screen. Here, if we subtract 3 to f of x and then we add 2 to f of x, then our function becomes y is equal to f of x minus 3 plus 2. So finally, our new equation is y is equal to modulus x minus 3 plus 2. As we have seen that the geometric effect of subtraction was that our graph was shifted from origin to right 3 units, and then the geometric effect of addition of 2 is that our graph is shifted 2 units above. So finally, the geometric effect of this subtraction and addition to the function is that it translates the graph of y is equal to f of x right 3 units and above 2 units. The next topic to study is the reflection of x-y axis. You can see the definition of reflection on the screen. For reflection, replacing x by minus x in an equation gives the reflection of its graph by y-axis, and replacing y by minus y in an equation gives the reflection of its graph by x-axis. So we can say that if we have ordered pair as minus xy, then it's the reflection of xy about y-axis, and we have ordered pair as x and minus y, then it's the reflection of xy about x-axis. Or more precisely, to draw the graph of any function by reflection, you can consider another definition which is on the screen. Graph of y is equal to f of x and y is equal to f of minus x are reflections of one another about y-axis, and graph of y is equal to f of x and minus y is equal to f of x or y is equal to minus f of x are the reflection of one another about x-axis. Students, now we will draw some graphs to make you understand the concept of reflection. You can see an example of reflection on the screen. For the reflection, we will consider an under root function which is y is equal to under root x. To draw the graph of this function, you have this solid line which is on right hand side, which is representing the graph of y is equal to under root x. Here we perform an operation that we replace x by minus x. So our function becomes y is equal to f of minus x, and finally our new equation is y is equal to under root minus x. And the geometric effect of this change would be that it would reflect the graph of y is equal to f of x about y-axis, which is vertical line. So you can see that on the right hand side and on the left hand side, both graphs are the reflection of each other about y-axis. Here we will consider one more example which would be showing the concept of reflection as well. You can see that example on the screen. For this example, we will be considering the same function which is y is equal to under root x, and you can see the graph of y is equal to under root x in the first quadrant. We perform an operation that we multiply f of x by minus 1, and our function becomes y is equal to minus f of x. In this way, our new equation is y is equal to minus under root x. The graph of y is equal to minus under root x would lie in the fourth quadrant, as you can see. So the geometric effect of this change would be that it would reflect the graph of y is equal to f of x about x-axis. You can see the graph in the first quadrant and in the fourth quadrant are the reflection of each other about x-axis. Dear students, now we will consider an example which would be having the reflection and translation change as well. You can see that example on the screen. For the graph of this function, we will be considering our final function as y is equal to cube root of 2 minus x. And for the solution, first we will consider a simple function of y is equal to cube root x. You can see the graph of this function over here. If we perform an operation of translation, which is y is equal to cube root of minus x, you can see that this graph is the reflection of y is equal to cube root of x. And for the translation, we have y is equal to cube root of 2 minus x. You can see the graph of this function over here, which shows that translation has transferred this graph to 2 units to right. Dear students, now let's come to the next topic, which is scaling. But before scaling, let me tell you about the characteristic of translation and reflection. Then we will explain the definition of scaling. You can see that on the screen. Scaling, translation and reflection are called rigid transformations because they do not change the shape of the graph, but changes only its position. But scaling is the process which actually changes the shape of the graph. Here, if f of x is multiplied by a positive constant c, then the geometric effect is to compress or stretch the graph of f of x in y direction. A compression occurs if c is greater than 0 and less than 1, and the stretching occurs if c is greater than 0. This is called basically the vertical scaling by a factor c. You can see an example of vertical scaling by a factor c through a trigonometric function on the screen. This purple line shows the graph of basic function, which is y is equal to sine of x. If we multiply this function by a constant 2, then we get this light blue graph, and if we divide angle of the function by 2, then we get this dark blue line as the graph. So this is basically showing the vertical scaling of this graph by a factor c, where c is equal to 2 in this example. In the next example, we will consider the horizontal scaling by a factor c. So if we multiply a positive constant c, then the geometric effect is to compress or stretch the graph of y is equal to x in x direction. A compression over here occurs if c is greater than 0, and stretching over here occurs if c is greater than 0 but less than 1. So this would be called a horizontal scaling by a constant c. You can see the graph of this horizontal scaling through a trigonometric function on the screen. Here we have a function y is equal to sine of x as our basic function, and this purple line shows the graph of this function. If we multiply this function by 2, we get this dark blue line, and if we divide the function by the constant c, then we get this light blue line as the graph, which is showing the stretching and compression of a function or the graph by a constant c, which shows the horizontal scaling by a factor c, where again c is equal to 2 over here in this example. Dear students, in graphing, here a question arises that if we draw a curve or the graph in xy plane, must that curve necessarily be the graph of y is equal to f of x for some function f? But this is not always the case, that every graph which is drawn is the graph of any function. As I told you that the simple answer to this question is that every graph which is drawn in xy plane is not the graph of the function. To know whether a curve is a graph of function or not, we move to the vertical line test. You can see the definition of vertical line test on the screen. A vertical line test. A curve in xy plane is the graph of some function f if and only if no vertical line intersects the graph more than once. And if that vertical line would intersect the curve more than once, then it would not be considered as the graph of any function. Here we will consider some examples to have the vertical line test. If we have a graph of 4x plus 3y is equal to 12, and the graph of this function is shown by this blue line. Here again, if we draw a vertical line over here, so it's quite clear that this vertical line is intersecting the graph of this function at a single point. So we can conclude that this is a graph of a function. A very important example in vertical line test is the example of a circle. If we have drawn a graph of a circle equation which is x square plus y square is equal to 25, which is having a radius at 5, and if we draw any line in this graph, so you can see that this vertical line is intersecting the graph of this circle at 2 points, and same is with the second line. So this is obviously not a graph of a function. Dear students, let's move to our very last topic of today's program, which is even and odd functions. You can see the definition of even and odd functions on the screen. For the odd function, if we have a simple function y is equal to f of x, and if we replace x by a negative x, and finally we get a function y is equal to minus f of x, then it would be an example of odd function. For even function, if we replace x by minus x, and we get the same function which was our principal function, or y is equal to f of x, then it would be considered as an example of even function. To have more understanding of even and odd function, we will discuss some examples. You can see the example on the screen. If we consider a single function y is equal to 2 of x, on the right hand side you can see the definition of odd function. If we put x is equal to minus x in this function, so we get y is equal to 2 times minus x. And so we get y is equal to minus 2 of x, which finally gives you y is equal to minus time the same function, which shows that y is equal to 2x is an odd function. To understand the even function, we will consider another example which is on the screen. If we have y is equal to x squared plus 1, we have the definition of even function that if we replace x by minus x and we get the same function, then it is considered as even function. So here we replace x by minus x. So we have y is equal to minus x squared plus 1. Minus x squared gives you x squared. So y is equal to x squared plus 1 is an example of even function, which is same or which remains same even after replacing x by minus x. Now, as I told you that every graph is not the function of the graph, so every function is not an even or odd function. To understand this concept, we will consider an example which is on the screen. If we have a function y is equal to 3x minus 1, and we apply a chain that we replace x by minus x, so we have y is equal to 3 times minus x minus 1. Finally, we have y is equal to minus 3 minus 1, which is not equal to function. So if we have y is not equal to minus time f of x, so it's neither even nor an odd function. Dear students, that's all we had to study in today's program. Let me tell you a very brief summary that what we have studied in today's program. In today's program, we studied graphs of function, graphing function by translation, graphing function by reflection, graphing function by scaling, a vertical line test, and finally even and odd functions. I will join you in the next program with the next topic of domain and range of a function. Till that time, Allah Hafiz.